Okay, right now we will work on exercise set 15.7. Now this section is actually on the long side and maybe quite difficult for some of you. It was difficult for me when I first learned it. You know what? Let me share my video. Yeah, it was difficult for me when I first learned it because I need to imagine what they look like in 3 dimension, especially for the later part. For the earlier part, like here, I plan to do number 4 and number 8. It's basically just doing integration 3 times, right? Okay, but you will see as we progress, the difficult part arises when we start building or setting up the integral. Okay, so you will see that 10, 12, and 14, we get harder part. And then yeah, number 16, number 18 also. And if we have double integral, at least we have 2 possible order of integrations. Okay, dy dx, you integrate respect to x first, respect to y first, and then respect to x, right? Or if it is too hard to do, then we integrate respect to x first and then respect to y. Okay, so when we have 2 variables, the domain is 2-dimensional, then there are 2 orders of integrations. However, when it comes to triple integrals, we have 6 different orders, 6 different orders, dc dy dx, dc dx dy, dy dc dx, dy dx dc, and dx dc dy, dx dy dc. Not to say that we may have another type that where we do r dr d theta and then dc, or other possible variations from there. We talk about this later though, but just for these sections we have 6 different orders. Okay, and that makes us that requires us to be able to imagine that in 3 dimension, and 3 dimensions, and see which order will be easier to integrate. Okay, yeah, so I promise you this section is not easy, so if you find it to be on the harder side, you are very normal. Okay, let's start with the easy part first, the one that we need to compute the triple integral, number 4. So triple integral of 2xyz dc dy dx for x from 0 to 1, y from x to 2x, and the z is from 0 to y. Now, before I go on, let me explain this first. The outer integral has to be by constant limits for the outer integral. Okay, now for the middle integral, it should be either constant, or if it contains variable, it contains variable for outer integral. So the middle integral here cannot has the middle integral limits, the limit of the middle integral cannot have y, cannot have z. Okay, now the innermost integral, let's see which color is good. Let me use this one here. The innermost integral, the dc, may have constant, may have y, may have x in the limits of integration. You cannot have z. You cannot integrate respect to z and then plug that z in. No way. Okay, so the innermost integral can use any variable. The limits of innermost integral can use any variable except for the variable of integral, the variable of the inner integration. Okay, the middle integral, the limits of middle integral may consist of constant or variable of the outer integral. How do I say it? Okay, the DC here, the innermost integral, can have y and x. This can have y, can have y and x. Okay, now the middle integral, the dy, can have x, which is the variable of the outer integral. Now the outer integral can only have constant. Okay, maybe I write it down. The limits can only be constant. Okay, the middle integral limits can contain x, which is the variable for the outer integral. Okay, now the innermost integral limits can contain y and x. Okay, now I will erase this because I will work on the integration. So you will only see this if you watch the lecture video. If you watch this as a video instead of you only see the PDF. Okay, let's start. So this is integral from 0 to 1, integral from x to 2x, xy squared from 0 to y of dy dx. When I replace the z by y, I get integral from 0 to 1, integral from x to 2x, xy times y squared dy dx. Right? It's supposed to be y squared minus 0 squared. Okay, but this then equals to integral from 0 to 1, integral from x to 2x of xy cubed dy dx, which will give us 1/4 xy to the 4th from x to 2x dx. That's 1/4 integral from 0 to 1 of x times 2x to the 4th, that's 16x to the 4th minus x to the 4th dx. That's 15, right? So this is 15 over 4 integral from 0 to 1 x to the 5th dx. Okay, let me turn off the camera. You don't need to see me. And then when I integrate that, that will give me 15 over 4 times 1/6, because it's supposed to be 1/6 x to the 6 from 0 to 1. But you know, polynomial from 0 to 1 is just the coefficients, right? So I skip that little step there. Reduced by 3, that will be 5. Reduced by 3, that's 8. Okay, I think this integration is quite easy. It's long, but it's not hard, right? Each step is you do single integration 3 times, right? Okay, I don't think that part is on the hard side. You know what? Let me do number 6. Let me try to do number 6. So I make myself work a little bit harder. Number 6, integral from 0 to 1, integral from 0 to 1 again, integral from 0 to square root of 1 minus c squared. Z over y plus 1 dx dz dy. So integrate with respect to x, but the integrand has no x. That will just be the length of the interval. Okay, and then I think I will do u substitution. Okay, I do that u substitution, so u equals to 1 minus c squared du equals to negative 2c dc. U at 0, for c equals to 0, the u is 1. For c equals to 1, the c is 0. So my integral right now becomes integral from 0 to 1, integral 1 to 0 of u to the power of 1/2 over y plus 1. And I will substitute the dc by, I will substitute the z dc by du over negative 2. Du over negative 2. Absorb the negative sign and take the 1/2 out. Integral from 0 to 1, integral from 0 to 1 of u to the power of 1/2 du over y plus 1. Actually, because y plus 1 is independent of u, you can pull it out also. You can pull out one integral. What I meant is you can rewrite it this way. I don't need to do it right now, but I can. You will see that's basically the effect. It actually looks like this. Okay, I can this, how to say that, this is independent of y. Well, in fact, if you think about this, oh yeah, that's right. Okay, yeah, this integral is now on rectangular domain, but the integrand is factorable, is separable. Okay, so we can actually go on even further and say we actually have this integration, right? Yeah, think about it. Just do it inside out and you will see what happened with the process. Okay, but this will then becomes 1/2 natural log of y plus 1 from 0 to 1 times 2 over 3 u to the power of 3/2 from 0 to 1. That's 1/2 natural log of 2 minus natural log of 1, but natural log of 1 is 0, times 2/3 times 1 minus 0, which is 1. So this is natural log of 2 over 3. That's for our number 6. Let's see number 8. Wow, I will do a lot of questions, huh? So that later on you have no reason to say, Thomas, you never teach this. Because I do a lot. And you will see that at the beginning of this section, you will see that it really depends on how patient you are to yourself. Okay? Please be patient to yourself though. That's the key. I know you're still in the learning process, right? So be patient with yourself in learning this. Okay, you are in Cal 3. It's not supposed to be simple. You know it's not simple. It's not easy. Passing this class will separate you from the bottom 90%, maybe even the bottom 95% of you will be in the top 5% in this college, you know. Okay, no, it's not easy. It's not an easy course. Okay, therefore be patient with yourself. Okay, it's doable though. It's doable. Okay, you will be even more. You need to be even more patient if your preparation in Calc 2 is weak. Okay, if your preparation in Calc 2 in Calc 1 is weak. Okay, I will do the inner integral first. This is in the basically integral of sine y. That's negative cosine y. So integral from 0 to square root of x. Integral from 0 to x. X squared negative cosine y from 0 to x z dc dx. That's integral from 0 to square root of pi, integral from 0 to x, x squared 1 minus cosine xc dc dx. How do I want to do this? Let me separate that. It seems like I may need to use two columns. So this is integral from 0 to square root of pi, integral from 0 to x squared dc dx. I think that one is easy to integrate, minus integral from 0 to square root of pi integral from 0 to x squared cosine xc dc dx. Right? The first integral, the integrand is independent of z, so it's just the length of the interval, 0 to square root of pi, and then that would be x squared times x dx. Later on, this will be integral from 0 to square root of pi x cubed dx. But don't detach your integrations, okay? Because we use equal sign especially, okay? Then we need to continue with this, okay? Minus integral, if I do u substitution, u equals to xz, then du equals to x dz. And u at u at 0 will be 0, u at x will be x squared, Okay, so my integral now from 0 to square root of pi, integral from 0 to x squared, right? Now I will use one of the x together with one of the x with dz to make it du. So now I have x cosine u du dx. Can you see that? Yeah, try to think of it this way. So if I rewrite this as x cosine xc times x dc, this will be my du, this is my u, right? X cosine u du. Now integrating that, integral of cosine is what? Sine, right? Minus integral from 0 to square root of pi, and then x sine x squared minus, supposed to be sine u from 0 to x squared dx, supposed to be like this, right? Okay, but that will give us integral from 0 to square root of pi x cubed dx. I will integrate that later on, minus integral from 0 to square root of pi x sine u x squared dx. And then I will do another substitution, right? Let me give myself more space here. This will be, if my u equals to x squared, no, don't use u anymore, use phi maybe, or w, maybe w. Phi looks like a u. So dw will be 2x dx. Thomas, why we cannot use u now? Well, because we used the variable u already as a dummy variable earlier, so don't use u anymore. Okay, so w0 is 0, w square root of pi will be pi. Okay, so this is integral from 0 to square root of pi x cubed dx minus integral from 0 to pi of sine w dw over 2. That's because x dx is my I have x dx, right, is my dw over 2. So this will be 1/4 x to the 4th from 0 to square root of pi minus integral of negative sign is positive cosine 1/2 cosine w from 0 to pi. Okay, so that will be pi squared over 4 plus 1/2 -1 minus 1. It's -2, so it becomes -1/2. So pi squared over 4 minus 1. Okay. That's for number 8. Again, I think at this point we are still okay with the integration. We need to do separation somewhere in between, right? In step number 2 to step number 3. Step number 2 to step number 3, I separate them. Oh, no, I'm sorry. I kind of like referred it wrong. From step number 3 to step number 4, I separate because one of them require substitution, the other one just regular polynomial. Okay, and then somewhere later on I still need to do another substitution. So instead of using u again, I use w. You can play with u or v as long as your v and your u looks very different, or you can use u1 u2 style. Okay, just make them different, please. Okay. So these 3 questions are basic triple integrals. Okay, now the later part we will struggle with setting up the integration. You see in number 10 here we have a triple integral over domain E. They use E as the continuation of D. D is the domain in 2 dimensions. E will be the domain in 3 dimensions. Okay, triple integral over domain E of e to the z over y dv, where the E is oh, this one is hard. The y is from 0 to 1. The y is 0 to 1. The x is from x equals to y to x equals to 1. And the z is from 0 to xy. Okay, this is the d here. Okay, which if you think about, this is basically double integral over d of e to the c over y. Oh, I'm sorry, another integral from 0 to xy. Okay, dc dA. I want to point out that this dA here is for this double integral. Okay, and then the inner integral here is for the dc. Okay, now and then if you think about that again, the d is basically integral from 0 to 1, integral from y to 1. Okay, integral from 0 to xy, e to the z over y, dx, dy, dc. I'm sorry, dc, dx, dc, dx, dy. The outer integral, the variable for the outer integral is y. This is the corresponding limits. The middle integral, the variable of integration is x. This is the corresponding limits. Okay, let's do the integration then. Integral with respect to c of this. I wonder if you can follow me. I will just do it in one step. I think you should be able to do it also right away. This is y e to the c over y from 0 to xy dx dy. I wonder if you can follow me. Yeah, do the u substitution. U equals to c over y, so du equals to 1 over y dz, right? So in other words, y du will substitute dz. Okay, now then when I substitute that in, I replace that integral from 0 to 1, integral y to 1 of y e to the x minus e to the 0, which is 1, dx dy, right? And then when we integrate with respect to x, I get integral from 0 to 1 y e to the x minus x from y to 1 dy. Okay, so this will be integral from 0 to 1 y. Okay, y times when x equals to 1, there will be e minus 1 minus when x equals to y, e to the y minus y dy. So this will be, let me separate this. This is e minus 1 integral 0 to 1 of y dy minus integral 0 to 1 of y e to the y plus y squared dy. Am I right? And this will be e minus 1 over 2, 1/2, right? Minus, let me integrate the y squared first. That will be minus 1/3. Actually, no, so it becomes plus 1/3. This is minus, yeah, that's minus. So this becomes plus 1/3. And then minus integral from 0 to 1 y e to the y dy. Oh, this one is integration by parts, huh? Yeah, integration by parts. 1 0 e to the y e to the y, so that will be e minus 1 e over 2 minus 1/6. Negative 1/2 plus 1/3 is 1/6 minus y e to the y minus e to the y from 0 to 1. E minus e minus 0 minus 1. So e over 2 minus 1/6, this becomes plus, becomes minus, minus 1. So e over 2 minus 7 over 6. I don't really like this, to be honest with you. Yeah, I don't really like this. You can check my computation, especially my integration by parts. but I think I'm okay. I think I'm okay. If I make any mistake, it must be algebra here. Okay, that's for number 10. Okay, let me go on with number 12. Let me give myself some space. Number 12. Okay, we have triple integral over domain E of sine y dv. For E lies below the plane, so the E is below below C equals to X, above the triangular region with vertices 0, 0, 0, 0, 0, pi 0, 0, 0, and then 0 pi 0. So this is the X, this is the Y, so this is the triangle. This is the D then. Okay, so for the D, imagine this E as D union, maybe I just do the integral right away. Double integral, this is for the D, okay, and this is from 0 to X sine Y dC dy dx, where the X is from 0 to 1, the Y will be from 0 to 1 minus X. Okay, think of it this way. Below C equals to X means it is above the plane, right? Above the triangular region with these vertices, you see that the C equals to 0, right? Up to Z equals to X. So this Z here is the one C equals to 0, C equals to X. Okay, that's why when you do substitution, remember somewhere in the past in your Calc 1 or maybe you're on Calc 2, you do substitution, you already change the variable of integration, but you don't change the limit of integration. No, that's not right. That's not right. Okay, once you do substitution, you need to also replace your limits of integration to, if you use u now, then later on it becomes u equals what, u equals what, like that. Okay, I know when you are in Calc 1, your teacher may not emphasize that, but he or she is supposed to still teach you the right way. Okay, now let's integrate this. Well, the dz, the integrand is independent of z, so that will be just the length of the interval. It's an x sine y dy dx. Now integrate with respect to y, that will be integral from 0 to 1 x negative cosine y from 0 to 1 minus x dx. I have that 1 minus x inside the... Oh, I don't like that. I don't like that. I don't like that. Oh, it's so hard to integrate later on. You know what? Change. Let's make it dx dy. This is dx dy. And this will be same thing, huh? Oh yeah, no, it's not same thing. 1 minus y dx dy. At least not that hard now. Yeah. Okay, integrate with respect to x, that will give us 1/2 x squared sine y. The x will be from 0 to 1 minus y dy. Okay, that's 1/2 integral from 0 to 1 minus y squared sine y dy. It's still hard, but at least not that hard. Okay, I think we need to do integration by parts here. So there will be 1/2 the derivative -2y, the derivative -2, and then 0. So integral sine y negative cosine y, negative sine y, cosine y. Oh wow. Okay, so the integral will be 1/2 times 1 minus y squared, negative 1 minus y squared cosine y, minus 2y sine y, minus 2 cosine y from 0 to 1. Let me make it nicer. That's y squared minus 3 cosine y minus 2y sine y from 0 to 1. When I plug in 1, I get, when I plug in 1, I get negative 2 cosine 1 minus 2 sine 1 minus, when I plug in 0, I get negative 3 cosine 0 is 1. That's what I have. Okay, so that is negative cosine 1 minus sine 1 plus 3. Okay, and the angle 1 here is in radian. Okay, the angle 1 here is in radian. I start thinking, should I check if this is the correct solution? Oh yeah, it's not, because it's supposed to be pi, not 1. I change it. I need to change it. So this is pi, this is pi, this is pi, this is pi. Good thing I check, otherwise I wonder why I get such an ugly answer. Y squared minus pi minus 2. Okay. I use 0 to 1, supposed to be pi. Okay, so this is 1/2. At pi, that will be pi squared minus pi minus 2. Cosine pi is negative 1 minus 2 pi sine pi is 0. So that's the first part. Minus, at 0, that will be 0 minus pi minus 2 cosine 0. That's 1 minus 0. Okay, so that's 1/2. 2 plus pi minus pi squared plus pi plus 2. Okay, so that will be pi plus 2 minus pi squared over 2. I hope this is the correct answer. Okay, I believe my integration is okay. No, my integration is not okay. My integration is not okay, so it should be here. Should be like this. What am I doing? So the derivative, good thing I checked, but at least 2 times pi minus y, the derivative of that is negative 2, 0. So this should be something with squared, and then this is minus 2 times pi minus y. Okay, now I need to, everything here is, everything after, let me redo it. Good thing I show my work, right? So that if I find a mistake, I can easily fix it. I would just plug that in then. Okay. At pi, the first term becomes 0. The second term is 0 minus 2 times negative 1. That's for the first term. For the pi. For the 0, that will be negative pi squared plus pi. I'm sorry, minus y0 is 0 minus 2. Okay, so that's 1/2. This is 2 plus pi squared plus 2. Okay, so pi squared plus 4 over 2. So I need to fix the pi, and I happen to substitute this x squared here incorrectly. I wrote pi minus y squared, supposed to be pi minus y, parenthesis squared. I did integration by parts 3 times, maybe only 2 times if you want to call that. I use tabular method. And then I substitute. That's what I get. Okay. Check my work though. Check my work. Don't trust me too much. Don't trust me too much. That's for number 12. See, I still have number 14. Huh? You can tell this section is hard because it's more into the tedious, being tedious. Number 14, let me copy that. Let me copy that number 14 here. Triple integral over domain E of xy dv, where E is bounded by parabolic cylinders, y equals to x squared and x equals to y squared. And then the plane C equals to 0, that's the xy plane. And bounded above by x plus y. So the domain in 2 dimensions is this. Okay, so triple integral by symmetry. Okay, so that will be from 0 to x plus y for the innermost integral of x, y, dz. Okay, and then dy, dx, this is 1, right? Integral from 0 to 1, the lower bound is x squared, the upper bound is square root of x. So that's the triple integral. Okay, because I come in, right, as the y increases, I come into that d from x squared and I exit at square root of x, right? Okay, then the integrand is independent of z, so that will be just the length of the integral, the length of interval. So xy times x plus y dy dx. That's x squared y plus xy squared dy dx, which when I integrate respect to y, that will be 1/2 x squared y squared plus 1/3 xy cubed from x squared to square root of x dx. That's for the y. Wow, that's a bit painful though. You know what? Let me continue here to save some space. So that is integral from 0 to 1 square root of x for the y. That will be 1/2 x squared times x plus 1/3 x times x square root of x minus, that's the upper bound, the lower bound x squared. So this is x squared x to the 4th plus 1/3 x to the 6th dx. So this is 1/2 x cubed plus 1/3 x to the 5/2. I make it into a fractional exponent right away so that it's easy for me to integrate later on. Minus 1/2 x to the 6th minus 1/3 x to the 7th dx. So that will be integral from 0 to 1 of a polynomial. So that's 1/2 times 1/4 plus 1/3 times 2/7 minus 1/2 times 1/7 minus 1/3 times 1/8. So 1/6 minus 1/24, 4 times 3/24 minus plus multiply by 2, that's 4 multiplied by 3, that's 1/42. U, that's 1/8 plus 1/42. I hope I know I make no mistakes here. What is the LCD? 42 is 6 times 7. I need to multiply by 4. 168 multiplied by 4 multiplied by 21. So that's 25/168. I really have no confidence in this answer. Okay, let me check my work again. I show you this because I don't know the solutions. I don't see the solutions yet, and I don't think I want to do that. Okay, instead of looking at the solution, I better check it myself. I believe my setup is correct. When I integrate that, this is what I get. Multiply x squared plus y plus x squared times y plus xy squared. When I integrate that respect to y, I get this and this. Substitute that in. Y squared becomes x, y cubed becomes x square root of x minus 1/2 x squared x to the 4th plus 1/3 x to the 6th minus plus integrate. So far I'm okay. Seems like here it's supposed to be 1/8. I find it. So times 3, so it becomes 2/24. So that's 1/12. So 84, huh? So that's 84. So So multiply by 2 and this one here by 7. So that's 9 over 84. We can simplify that. It's both of the multiple of 3. So this will be 3 over 28.
Hi.
Oh, good thing I check, huh? I hope I don't make other mistakes. But yes, I make silly mistake earlier. Okay, the 1/6 supposed to be 1/8. That's for number 14. Let me go on. The next one, number 16. As you can see, I don't think I will finish this 15.7 in one shot. It's not an easy part, and I prefer to do more problems. Okay, so I will do more in future, but this is my 15.7a. So let's do a couple more questions, maybe 2 or 3 more questions. Okay, number 16. Triple integral over tetrahedron T, number 16. Triple integral over tetrahedron T of x, y, z dv. Okay, where T is the solid tetrahedron with these vertices. Oh, shoot. Okay, 0, 0, 0, that's the origin. 1, 0, 0, 1, 1, 0, and then 0, 1, 0, 1. Oops, I don't like this view. Maybe I rotate that a little bit then. From the other side. So let's say this is our x-axis, this is our y-axis. Okay, 0, 0, 1, 0, 0, 1, 1, 0, and 0, 1, 0, 1. So not that one, not this thing here. It's this guy. This is 1, 0, 1. This is 1, 1, 0. Okay, this is 1, 0, 0. Okay, if I go back to the original view, what happened? Is 0, 0, 0, 1, 0, 0, 1, 1, 0, and 1, 0, 1. Okay. The thing is, we need to find the equations for this though. The equation for this is just xz plane, right? So y equals to 0. That is y equals to 0. How about this plane here? That is x equals to 1. Okay, the same plane with this, right? This is x equals to 1. Okay, that's x equals to 1. Now the thing is, how about this plane? How about that plane? Any idea how to get that plane? You do the cross product, right? So you create a factors. So you create this factor here and this factor here. You get the cross product, right? Okay, so let's call this phi1 and this is phi2, right? The plane contains these two factors, right? Okay, so that plane, the green plane, is perpendicular to the product of phi1, the cross product of phi1 by phi2. Okay, which is our phi1 is what, 1 0 1, and our phi2 is 1 1 0. I j k 1 0 1 1 1 0. The first component is -1, the second component is 1, the last component is 1. Okay, so that green plane is -x plus y plus c. It passes through origin, so it must be -x plus y plus c equals to 0. Okay, now let's see the domain on xy plane. On xy plane, it looks like this, right? On xy plane. So the outer two integral from 0 to 1 for the dx. For the dy, it will be integral from 0 to x. For the dz will be from 0 to c will be x minus y, x, y, z. Okay, so the integrand, what color should I use? The yellow. So the integrand xyc is here. Okay. Now let's integrate that. Let me move it here so that I can get two columns later on. Integral from 0 to 1, integral from 0 to x, 1/2 xyc squared from 0 to x minus y. So there will be x minus y squared dy dz. Now then integrate with respect to y. Should I FOIL this? I FOIL that. It's polynomial anyway. So this will be x squared y and x cubed y minus 2x squared y squared plus xy cubed dy dx. Integrate with respect to y will give us 1/2 x cubed y minus 2/3 x squared y cubed plus 1/4 xy to the 4th from 0 to x dx. Replacing y by x will give me 1/2 x to the 4th minus 2/3 x to the 5th plus 1/4 x to the 5th. Why I feel like something's missing? Oh, should be squared here. Oh, so I need to add the LCD thing equals to 1/2 integral from 0 to 1. What is 1/2 minus 2/3 plus 1/4? LCD is 12. So that's 1/12. So that's 1/12 x to the fifth dx, that is 1/2 times 1/12 plus 1 times 1/6, that's 1/144. Okay, that's for number what again? Number 14. Now notice that you are not able to do this integration if you cannot set it up, and you will not be able to set it up if you don't know how to get this green plane. Okay, so finding the equation of a plane, something that we learned in test 1 before test 1, therefore show up in test 1, show up again in this section, right? And it will come again and again and again. Okay, how to find that? So we get two factors, do the cross product, we get the factor normal to it, right? So the factor normal to this phi1 cross phi2 is somewhere like this. Okay, perpendicular to phi1, perpendicular to phi2. Okay, that's for number 16. I don't know if I want to do number 18. Should I do it? Let me copy that here. Okay, let's see this question. Honestly, I'm tired. I'm tired, but let's do it anyway. If it is tiring for me, then it must be for you also. Okay, but if I want to teach you to be patient, to preserve, then I need to do that too, right? Okay, z dv. I need to set up the integral where E is bounded by the cylinder y squared plus z squared equals to 9. Oh, that's parallel to the x-axis, huh? That's parallel to the x-axis. So that is actually a cylinder that goes this way. Okay? This is the sketch. And then the planes x equals to 0, that's the YC plane. X equals to 0, that's the XY plane. And y equals to 3x. Y equals to 3x. Y equals to 3x. So y equals to 3x. Looks like this then, huh? So the domain will look like this. This is the domain on xy plane. Okay, but it goes up and down though. It has up. Oh no. Only in the first octant. So yes, it goes up only. So if I go back to this picture here, let me use blue, black color then. It will be something looks like this. That's what it looks like. Maybe if I see that from behind, so let's say this is the x-axis and this is the y-axis. Is it a better view? Not good, not good, not a good view. Maybe this way then. So if this is your x, this is the y, this is the c. On the domain, this is y equals to 3x. This is part of the cylinder. This is also part of the cylinder. So this is what the solid look like. Okay, so if we set it up, how will we do that? I think I will integrate from 0 to 3 for the dy, and as for the dx, that will be from 0 to y over 3, and as for the z, that will be from 0 to positive square root of 9 minus y squared of z. You know what? I don't like this. I don't like this. You can just integrate from here. Let's do it. Let's do it. So this is 1/2. I will do it another way after this. So this is 0 to 3. Integral from 0 to y over 3. C squared from 0 to square root of 9 minus y squared dx dy. This is 1/2 integral 0 to 3 integral from 0 to y over 3 9 minus y squared dx dy. The integrand is independent of x, so there will be just length of interval. So that's 9 minus y squared y over 3 dy. That is 1 over 6 integral 0 to 3 y times 9 minus y squared dy. Okay, I think you can take it from there, right? You should be able to take it from there. This is, I will compute that, but for the purpose of comparing the result later on with another technique. Okay, so this is 1/6 that's 1/2 9/2 y squared minus y cubed, so it becomes 1/4 y to the 4th from 0 to 9. I'm sorry, not 0 to 9, 0 to 3. What am I doing? So that's 1/6 81 over 2 minus 81 over 4. That's 81 over 4. That's 27 over 8. Now, the other method I want to teach you is the following. If you take a look on this graph here, right, and you take a look on the shadow of the solid on YC plane, the shadow of the solid on YC plane, it's basically a circle, a quarter circle with radius 3, right? Okay. Goes in the x direction with equation y equals to 3x. Okay, so I can actually rewrite the integral using polar from 0 to pi over to 0 to 3. Okay, where I say the y is r sine theta, r cosine theta, and the x is my r, the z is r sine theta. Okay, so the integrand here becomes r sine theta for the z. Okay, now while the x will be from 0 to y over 3, which is r cosine theta over 3. Over 3, not over 2. So, what I want to say is this region here give us this domain of integration. Okay, this is my z. Okay, that's my Z with RD theta for the middle and outer integral. The inner integral, it's still dx, right? Now let's try to integrate this, and I believe we're supposed to get the same answer, 27/8, unless I make some miscomputation. Okay, let's try. Okay, when I integrate with respect to x, it's independent of x, so it's just the length of the interval r sine theta r cosine theta over 3 r dr d theta. The nice thing about this is the domain is already quote-unquote a rectangle, all constants, right? Okay, and I can take the 1/3 out integral from 0 to pi over 2 of sine theta cosine theta d theta integral from 0 to 3 of r cubed dr, right? So that is 1/3 times 1/2 sine squared theta from 0 to pi over 2 times 1/4 r to the 4th from 0 to 3. So this is 1/6 times 1 times 1/4 times 3 to the 4th. That's 81/24 reduced by 3. I get the same thing. Okay, in other words, I still use polar, but instead of using polar against xy plane, the r theta from xy plane, I use yz instead to r theta. Okay, and I think the integration is a lot easier to do, as you can see earlier, right? Okay, that's for number 18. Yeah, the setup is hard. For us to set up the integration, the triple integral, you need to know what the solid, approximately what the solid look like. Okay, now if the solid happens to be a nice thing, if you project that to one of the plane, in this case, it gives us a quarter disk, right, on YZ plane in the first octant, then you can polarize that, use polar integration instead. Okay, now if you still use XYZ coordinate integration, you see we still get the same result. It's just harder, a bit harder. Okay, a bit longer, I should say, but not harder. Okay, how about number 20? Number 20, use a triple integral to find the volume of the given solid. We just need to find volume, but the time is already there. I think I will stop here and then I will continue in the next meeting or in the next supplemental videos. I plan to do a couple more questions. Number 22, 24, 27, 28. This is a long one though. And then 30, 32, and number 34, 36, and some more. Yeah, so this may worth another long supplemental video. I will stop here. I will continue in 15.7b for this section.